based on the fact that when theta equals 0, you're up at 4, and then that's going to be theta equals pi over 2, right there. And so this is that area that I have in red. So what I'm going to do is do that. Does that make sense? Say that one more time. Alpha?
Yeah.
Just because I didn't want to write 1.318 on 16072 again and again, I define that as alpha. Just now that it's written that that's alpha, whenever I use alpha, everybody knows what alpha is. It's 1.318 something. Right? Yeah. How many of you do not see where this comes from? And it's totally fine because this is the first time that this is our first problem in it. So if you don't, be honest with me. I just want a feel of where we're at. How many of you don't really understand where this is coming from? Raise your hand. Okay, so as a quick reminder, I would say this. The area is equal to, the formula is this.
Okay.
And that comes from the area of a sector formula, right? Because we're using that in many of those on the finite element. That's where the 1/2 comes from. I'm doubling because it's on top and down below. Meaning if on the x-axis, I have the same region up here and down there. So I'm just finding the green plus red and then doubling that. And that's what I need to subtract from that big pink circle. Yes? Because, so I know that it's going to start out at this theta value, but then the next theta value is where the pink hits the pole or the origin, right? Well, and R represents how far you're away from the origin. So if you're at the origin, R is 0. So I was saying, what theta value makes the R value 0? Pi halves. Does that make sense?
Yeah.
Ish?
Why were you using 4 cosine theta instead of the integral for that?
Okay, so my analogy is this. So just bear with me and I will totally answer that question. Remember when we had, if that was f of x, and then this guy was g of x, and I wanted the area from, let's say, A to B, right? Well now, because we have functions here, we're in the rectangular coordinate system, I'm going from the lowest value all the way to the upper, or the greatest value, and I'm moving to the right. So this right here is where the one that is closest to the x-axis changes, right? So I would go, let's call this x of 1. So on this region, I would go to the black function. And then I'd have to switch. And then I'm going from that value all the way to this of going up to the blue function. Remember when I did that? So this is a perfect way to think about it because you're going to whatever's closer, right? So now let's go back to this problem that we just did. So what's closer to the pole? Because instead of going out from the x-axis up all the way, we're going out from the pole, and it's like, right, as it's sweeping through. So what's closer to the pole? So for any theta value, if I were to take like a random, like right here, and say, boom. So at that theta value, what's the one that's closer to the pole, blue or pink? This is the pole. On here, what do I hit first? Blue, right? So this is the pole, so what's closest on this line? Meaning, what does the line hit first? Blue and then pink. So I'm going out to blue. So now, it's kind of tough to see right here, but I'm going to do the same thing going like right there. What do I get to first? The blue or the pink? The pink. The pink is in here, the blue is out there, right? So you're going out to whatever's closest to the pole, which in this case is the pink where I have it red. That's why I changed colors from green to red, because the polar curve that I'm going out to switches from the blue to the pink for what's closer that I need to subtract from the entire area. Does that make sense?
No question about a different problem.
Okay. Now, here's what I want to say. You ready? Just like how Marcus said, well, why didn't you go from negative alpha to alpha of going out to the blue? I absolutely could have. But then you'd have to find the other limits of integration. So really somebody might have that this is 4 pi minus 1/2 times the integral of, or from negative pi halves to negative alpha of 4 cosine theta squared d theta. And then you'd also have to subtract, or if it's in parentheses, then adding to what needs to be subtracted, the integral, or 1/2 times the integral from negative alpha to alpha of 1 squared d theta. And then you'd have to subtract, or add if it's in the parentheses, 1/2 times the integral from alpha to pi halves of quantity 4 cosine theta squared d theta. Do you see what you're doing? You're just deciding to go and treat each, so treat that separate, and then from there all the way to there, it's the same, blue is closer, and then from there to there. So you could do it that way, piece it out, or deal with the symmetry and say, I'm going to subtract out this, and then double that, and subtract out that whole area. That's how I approach this problem. Yeah? It's tough.
One question.
Yeah.
For the black equation, I'm confused why you're adding stuff in parentheses and not subtracting it.
So what I'm doing there, when I'm adding, is I'm saying, take this plus that, and then double that, and then subtract that whole thing from this. Still not?
I thought you were trying to take away part of the area because it wasn't in the circle. Kind of like, I'm kind of losing it because you covered everything up in there.
Cool. Let's say this. You ready? Can I fill? I said, give me the area of this circle minus whatever's, give me the area of what's blue. What I would do is this. I'd say area of circle minus area of triangle plus area of rectangle. Do you see that? If you distribute through the negative, the minus, then it's the area of the circle minus the area of the triangle minus the area of the rectangle, which is the same thing as adding those together to get the total area that needs to be subtracted, and then the area of the circle minus what needs to be subtracted. Blow this up. Awesome. Okay, absolutely. I'll send someone down. Thank you so much. All right, bye. We both said thanks so much at the same time.
Wow.
What a coincidence. Does that make sense? Does that answer your question? Cool.
Just